Pre-calculus 5.3, day 2 notes. So continuing to solve trig equations. And so you saw in the last section, of function that was an equation that was quadratic, and it was probably, I don't know if it was in sign, but you saw one. And here's one that's quadratic in terms of secant. And so in our first example, we have one that's quadratic in terms of cosine. And so we're going to factor this just like we would a quadratic expression, only it's got trig stuff in it. So on this first one right here, we're going to factor it, set equal to 0, so we're ready to go ahead and factor it. And if it helps, off to the side, you could do it in terms of just c, and I need a 2c and a c, and then things that multiply to be a positive 2, but add up to a negative. That means both the signs are going to have to be negative, and I need it to be 5, so I'm going to put the 2 here and the 1 here. That would give me that minus 4c minus, that would work. Only I'm going to do it in terms of cosine, so you have to show it in terms of cosine in the work that you present as your solution. So if you do this, you've got to do that off to the side. I don't want it mixed up within the problem. So here we have a 2 cosine of x and a cosine x. To get a positive 2 but negative 5 in the middle, they both need to be negative. Put the 2 here and the 1 here. And then we have this 2 quantities equaling 0. That will only happen if one or the other is 0. It's called the zero product principle that I talked about in the notes last time. So now you're going to isolate the trig function. So add 1, divide by 2, and I need the solutions where cosine is 1/2. But I am now limiting just from 0 to 2 pi. So between 0 and 2 pi, cosine hits 1/2 only in 2 places. So you got to watch the directions. So instead of infinite solutions, it's only within that one rotation, that unit circle. And cosine is 1/2 in quadrants 1, and it is the pi thirds, and in quadrant 4, which is the 5 pi thirds. That's where you're going to get points on the unit circle where you go the right 1/2 and up root 3 over 2, or you go to the right 1/2 and down root 3 over 2. Those are the 2 places where your cosine's 1/2. So this is going to be x's pi thirds, or the quadrant 4 with reference angle 5, or pi thirds is 5 pi thirds. And there's no plus 2 pi n because we're only looking for solutions between 0 and 2 pi. And then on the next one, we have cosine of x equals 2. Well, if you think about the graph of y equals cosine of x, okay, that should go down a little bit further, but it's going from 1 to -1. And the range, the output, is only from -1 to 1. There is no place where cosine hits 2. This is not possible. There is no angle that you can put in cosine and get the output to be 2, because the normal range of cosine is -1 to 1. So that doesn't produce any solutions. So these are your only 2 answers. All right, well, that was nice in example 1. Everything was in terms of cosine. But there will be quadratics where they are not in the same trig function. And so you need to use your identities to get them into the same trig function so that then you can factor. And so on this one, you see cotangent squared, you see cosecant squared. And so I'm thinking 1 plus cotangent squared x is cosecant squared x. It's that Pythagorean identity. And so you can go either way. It really doesn't matter. I just so happen to think about it this way, where cotangent squared is cosecant squared x minus 1. So I'm going to go ahead and do it that way. So in for cotangent squared, I'm going to put what it's equal to and replace it with this. And so replacing cotangent squared with that cosecant squared x minus 1, and then I have the rest of this. And so the cosecant squareds are like terms. There are two of them. And the minus 1 and the minus 7 are like terms. So collect them. And then isolate the trig function. And divide by 2. And then when you take the square root, you get cosecant of x equaling plus or minus 2. And what we're going to do, you can do cosecant, but I think most people, cosecant is the reciprocal of sine. So if I think of this as one, replace cosecant with 1 over sine. And then on the right side, think of this as over 1. And a property of proportions is you can just flip both sides. So I get sine x over 1 is 1 over that plus or minus 2. That means sine of x is plus or minus 1/2. And the angles that make sine either positive or negative 1/2 are going to be the solutions. And so where is sine plus or minus 1/2? Well, those are 30-degree reference angles, quadrants 1 and 2, that make it positive 1/2, right? Root 3 over 2 and up 1/2, or negative root 3 over 2 and up 1/2, or where it's negative 1/2 is quadrants 3 and 4, which are that negative root 3 over 2, negative 1/2, and positive root 3 over 2, that's root 3, negative 1/2. So I need all places where sine is 1/2. And so this is going to be where it's positive is pi 6. And this didn't have a restriction on the domain. So it'd be pi 6 plus 2n pi, x equaling 5 pi 6 plus 2n pi, x equaling 7 pi 6 plus 2n pi, and x equaling 11 pi 6 plus 2n pi. And that's where n is an element of the integers. So there you have all of the solutions. Now, it just so happens that since I want where it's both positive and negative, from quadrant 1 to quadrant 3, it's a half a turn. It's an addition of pi. So I could actually take care of those two by saying x is pi 6 plus n pi, n an element of the integers, and that would get the quadrant 1 and the quadrant 3, one place where it's positive 1/2, one where it's negative 1/2, and multiples of that. And then in the same fashion, between quadrant 2 and quadrant 4, there's a half turn. So for that, I could use the 5 pi 6 plus n pi, where n is an element of the integers. And then, oops, that's going to be a more concise way of writing the answers. And I mention that for two reasons. This shows a better understanding of the math. But the other reason is you might get this, and this might be how they write the answer, and you need to realize that they're the same. So if you get 4 and they have 2 answers all of a sudden, or if you have 2 answers and they have 1, you just want to question, was there a way that they could combine those where really our answers mean the same thing? And we gave infinite solutions here because I didn't put a restriction on the domain. All right, so example 3. Sometimes we have to apply the technique of technique of squaring so that I can make substitutions to get things in the same trig value. And this is what's happening in this third example. It says find all solutions in this interval. So we're not going to have to worry about the multiple angles, but we need all solutions of this equation within one full rotation, within one unit circle. But the problem here is secant's not squared and tangent's not squared. And by the way, 1 plus tangent squared x equaling secant squared x, I still think that there's people who do not understand that this does not simplify like this. This is not true. You can't do this. The square root of a squared, oh, come on. The square root of a squared plus b squared is not a plus b. It doesn't work that way. And so one thing that I often show with this, if you had 3 squared plus 4 squared, is that equal to 3 plus 4? Does that become equal to 7? Well, this is 9 plus 16, which is a square root of 25, and 5 is not equal to 7. The square root of a squared plus b squared is not a plus b. They are not the same thing. So the same thing with the Pythagorean identities, you can't think that the square root of 1 plus tangent squared is 1 plus tangent x. So that was a little detour there, but it's important. We are going to be using the 1 plus tangent squared equals secant squared. We're just not quite ready for it because that's why we have this need to square both sides. So we can get some tangent squareds and secant squareds. So now I'm going to square both sides. Now when I square both sides, I can get some extraneous roots. So I need to make sure I check answers at the end. And also when I square 1 plus secant of x squared, that means foiling 1 plus secant of x times 1 plus secant of x. And if I distribute my 1, I get a 1 plus secant x. If I distribute the secant, I get another secant x plus secant squared x. When I square that, I get a 1 plus 2 secant x plus secant squared x. It is that special property when I have a plus b and I square it. Oh, come on. You get a squared plus 2ab plus b squared. You get a trinomial. The square of a binomial is a trinomial. So a lot of detours here, just talking about some algebra skills that you need. And so when I square 1 plus secant squared, I get 1 plus, square it, multiply and double it. Square the 1, multiply the 1 times secant, but double it, and then square the secant squared, or the secant. That's that special property of a plus b squared. And then tangent of x squared, we're going to write tangent squared of x. All right, and so now I've introduced some secant squared and tangent squared so that I'm ready to apply this in some way. The problem, I want to get it into one trig function. And so I'm going to replace tangent squared, if I rearrange this, with secant squared x minus 1. And the reason why I'm going to go that route is because I don't have a way of replacing secant to the first in terms of tangent, and I want to get them all in the same function. So the best way to do that is replace the tangent squared with secant squared x minus 1. Then everything's in secant. So I'm going to have 1 plus 2 secant x plus secant squared x equals secant squared x minus 1. Now that it's all in the same trig function, I can continue to do the algebra and solve. And in this case, I have secant squared on both sides, so those are going to cancel. So I have 1 plus 2 secant x equaling a negative 1. Don't forget that negative 1. I want to isolate the secant, so subtract 1. And I have a minus 2. Divide by 2. And I want to know where secant x is negative 1. Well, secant is that reciprocal of cosine. And if you think back graphically to cosine for just one period, here's pi halves, here is pi, here's 3 pi halves, and then we're back at 1 at 2 pi. And when you graphed the secant, where cosine was 0, you had vertical asymptotes. And since secant was the reciprocal of cosine, secant graphed like this, and they met up in the spots where cosine was 1 or negative 1. So secant's going to be negative 1 at pi. So there's one way to think about it. Now, that's not the only way to think about it. Similar to I did in a different problem, we can remember secant is 1 over cosine x. So secant's 1 over cosine. So I can replace secant with 1 over cosine, and I still have a negative 1 on this side. But then I can think of negative 1 as over 1. And then a property of proportions, I can flip both sides. So I get cosine x over 1 equals 1 over negative 1, or cosine of x is negative 1. So this becomes the same as solving where's cosine of x negative 1. And then you can think, where's cosine negative 1 on the unit circle? And since it's the x value, you should think it's at pi. So my solution to this is x equals pi. But you should check for extraneous because maybe there's no solution at all. And you do that by plugging pi into the original problem. And bring down that original problem, which was 1 plus secant of x equaling tangent x. And I'm going to plug it in because there might not be any solution. So I have 1 plus secant of pi plus tangent, or not plus, equal tangent of pi. And secant of pi is negative 1, because up here, this is the unit circle value, and secant is hypotenuse, which is 1 on the unit circle, over x, you get 1 over negative 1, it's negative 1. Or from the graph that I showed up here, right here, secant is negative 1 at pi. And then tangent of pi is your y over your x. So again, on the unit circle, you have negative 1 over 0. And so your y over x is 0 over negative 1, which is 0. So tangent of pi is 0. You get 0 equals 0, and they check. Notice I haven't picked up any graphing calculator. It's all doing this, no calculator, just things that you're supposed to know. X equaling pi is the solution. So watch on the homework if there's an interval where you don't have to do infinite solutions versus if there isn't an interval and you have to. And try to do this without outside help and practice your unit circle values.